Hello everyone. So in the last class we were discussing about phase shifters and coaxial connector and uh, the attenuators, right? So today we'll continue with the discussion based on the waveguide Tees, which is going to be the next topic. Okay, so these waveguide Tees junctions are used to split the line power into two or combine the power from two lines with proper consideration of the phase. That is, it may split the power into two halves, or from two ports it is going if the power is fed means it is going to combine them, okay, with the proper consideration of the phase. The junctions that are widely encountered in the microwave techniques are E-plane, H-plane, E-plane, H-plane T, and the magic T. So we'll first discuss about the E-plane. So this E-plane T is designed by fastening or by securing, okay, a piece of similar waveguide to the broader wall of the waveguide section. You can observe in this figure, right? So similar waveguides are taken, right? So to the broader wall of the waveguide, we are going to attach this. This is the broader wall of the waveguide. Okay, to that we are connecting one more waveguide here. Okay, that is the meaning of securing this another waveguide with the broader section of the one waveguide, right? The secured waveguide is called the auxiliary arm. So this we are securing, right? Um, so this is going to be called as the auxiliary arm. So this waveguide we are securing, right? So this is going to be the auxiliary arm, and it is parallel to the plane of the electric field of dominant mode TE10 in the main waveguide. It is shown here. So as the axis of the side arm is parallel to the electric field, this junction is going to be this junction is called as the E-plane T junction. So this is parallel, whatever the side arm it is there, okay, side arm or series arm we are going to call that as, either side arm or series arm we call. So as this axis of the side arm is parallel to the electric field in this junction, so it is named as the E-plane junction. Okay, E-plane T junction. So in the figure it is showing the propagation of electromagnetic fields in the E-plane T when the dominant mode T10 is incident on the symmetrical port 3. While passing through the junction, the electric lines of the force bend, and as a result of this, fields of opposite polarity emerges from two arms. As the signal we pass here, it has to bend here at this position. Okay, so what is happening? The electric lines of the force bend, and the result of that, as a result of that, the fields of opposite polarity emerge from these two arms. Okay, if the fields of opposite polarity are fed um, into the two arms 1 and 2, this is 1 and this is 2 and this is the arm 3. If the fields of opposite polarity are fed into the two arms, that is port 1 and 2, the fields in the symmetrical arm are added. So from here and here, if you are going to send the signal, means they are going to be added up. Okay, at the port 3 we are going to receive the signal. If the fields of same polarity are fed into the two side arms, they emerge out the symmetric arm in opposite phase and therefore cancel out the effect in each others. Okay, so it is given here. So this is given here. If the fields of the same polarity are fed into the two side arms, then there emerges the symmetric arm in opposite phase and therefore cancel out the effect of each others. Okay, so the effect of each others will be cancelled. So you can observe in port 1, so it is in this direction, and here it is at port 2, the direction is like this. Okay, so they are going to get cancelled with each other. Hope you understood. So the analysis of E-plane T using S matrix. This is important. So consider the 3-port microwave junction having a scattering matrix. So that is given like this. It is a 3 cross 3 matrix. So S112, S33. Suppose if we are going to consider the junction is perfectly matched, then there are no reflections at the ports. So we can write S11 is equal to S22 is equal to S33 is equal to 0, as there is no reflections at any ports. So S11, S22, S33 can be taken as 0. As the S matrix is symmetric and unitary, so what we can write, S12 is equal to S21, S13 is equal to S31, S23 is equal to S32. Therefore, their complex conjugate S11 into its complex conjugate, S12 into its complex conjugate, S13 into its complex conjugate becomes 0. So if you take an example for lossless junction, then we'll have S11 into S11 conjugate, S21 into S21 conjugate, S31 into S31 conjugate is equal to 1. Similarly, S21, S22, S23 with their conjugates multiplied with their conjugates, it is 1. S31 plus S32, S33 with their multiplying with their conjugate terms, we are going to get a unit. Okay, so you can observe the equation number 2, that is S11 is equal to S22 is equal to S33, right? And observe this equation and this equation. Okay, so compare this this equation and this equation 274. Okay, so 274 and 272, if you compare, then what we are going to get? So if you compare those two equations, is it visible? If you compare 272 and 274, that is 272 is S11, S22, S33 is equal to 0, and I'm comparing this with the S11 and its conjugate, S22, S12 it's into the S22 conjugate, S13 and S32 conjugate. So if we compare these two equations, what we are going to get is S11 means it is equal to 0. So this term becomes 0. S22 means here, even though it is conjugate, it is going to be considered as 0 itself. So we are left out with S13 into S32 is equal to 0. The same thing, by comparing that two equations, we are going to get S13 into S32 is equal to 0. By using the equation, that is S11 is equal to S22 is equal to S33 is equal to 0, and this equation S11, S21, S31, the sum of these three, we find that that can be written as S12 square is equal to 1 minus S13 square, or it can also be written as 1 minus S23, as S13 is equal to S23, right? So 1 minus S23 square. So in case of E-plane T, the output ports, the output at the ports 1 and 2, the output at the ports, so we can observe here, the output at ports 1 and 2 are out of phase by 180 degrees. Are there, as we know, the signal coming here will have to bend. So in opposite polarities, we are going to get the outputs on two ports. No? So they are going to be out of phase by 180 degrees with input at port 3. Okay, when compared to the input at port 3, the waves here are 180 degrees out of phase. So the scattering coefficient is given by, the scattering coefficient is given by S32 is equal to S23 is equal to S13, that is with minus sign, as it is 180 degrees out of phase. So the scattering coefficient is given by S32 is equal to S23 is equal to S13, right? Minus of S13. If port 3 is perfectly matched to the junction, then port 3 is matched to the junction, then S33 becomes 0. So if you are going to check the above properties, that is from equation 273. So 273, these conditions along with that, so those conditions along with this condition S33 is equal to 0, we can write the S matrix as S11 is S11, S12, S13, but S23 is minus S13 in the last equation we have seen. So that is substituted here, and S33 is 0. So from unitary property, we know that the matrix with its complex conjugate is going to be unity. So substitute that S and its conjugate term is equal to 3 cross 3 unit matrix. So multiply the rows and columns here. Row 1 with column 1, row 2 with column 2, row 3 with column 3. So we are going to get these three equations, right? These three equations. Again, we are going to multiply the row 3 with the column 3. Okay, there we are going to find S13 into S11 conjugate and minus S12 conjugate is equal to 0, or it can be written as S11 is equal to S12 is equal to S22, right? This thing we have seen. So from these two equations, compare these two equations. So S11 is there, S12 is there, S12, it may get cancelled, right? So S13 is there, S13, it will also get cancelled. So we are left out with S11 square is equal to 1. Okay. So yes, one second. So comparing these two equations means S13 cancels, S12 cancels, and we left out with S11 and S22. But from this equation 2715, S11 is equal to S22. So in this equation, when we compared these two equations, we are left out with S11 square plus S22 square is equal to 1. So for S22, what I'm going to write is, I'm going to represent that by S11 itself from this equation. Okay, so 2S11 square is equal to 1 we are going to get. Okay, or otherwise S13 is going to be equal to 1 by root 2. Okay, so compare 1 and 2, you'll get this thing. Okay, S13 is equal to 1 by root 2. So if by using this condition, okay, this condition to this condition in equation, the first equation, this one, row 1 and column 1 equation. So as we know, S11, S12, S13. So if we are going to substitute that here, then we are going to get S11 square plus S11 square plus half is equal to 1. Okay, so as S11 is S11, S12 is also S11. Okay, S13 is 1 by 2, S13 square. So square means it is going to be 1 by 2, right, is equal to 1. So 2S11 square is equal to 1 by 2. This implies that S11 is equal to 1 by 2, right? So from equations 2714, 2716 and 2717, from these three equations, that is where we have S11 is equal to S12 is equal to S22, again S13 is equal to 1 by 2 and S11 is equal to 1 by 2. With these three equations, we can write the S matrix as S matrix can be written as S11 is 1 by 2, S12 is 1 by 2, S13 is 1 by root 2, right? Likewise, we are going to substitute the values. So we know that the scattering matrix is defined by S is equal to B divided by 8, where B is the output and A is the input. So in the B form, that is output is equal to the S matrix into the input matrix. Okay, so we are going to get it as B is equal to, in the matrix form, it can be written like this. So B1 is equal to the sum of the row 1 and this column. B2 is equal to row 2 and this column. B3 is equal to row 3 and this column. Okay, so there are 3 more cases. So what is the case 1 is, when an input at port 3 equally divides between port 1 and port 2 but introduces a phase shift of 180 degrees between two output. Hence E-plane T acts as a 3-bit splitter. Okay, so this thing we have seen. So whatever the input that we provided port 3, it is going to be divided among port 1 and port 2, and it is also having a phase shift of 180 degrees between two outputs. Okay, so E-plane acts as a 3 dB splitter. So A1 is equal to, A2 is equal to 0 we get, and A3 is equal to, A3 is not equal to 0. Therefore, from equation for B1, okay, B1, B2, B3, we have B1 is equal to 1 by root 2 A3, B2 is equal to minus 1 by root 2 A3, and B3 is equal to 0. Okay. Case 2, when equal inputs at port 1 and 2, when equal inputs at port 1 and 2 result in no output. Suppose there are no outputs at port 1 and 2, then what happens? A1 is equal to A2 is equal to A, and A3 is equal to 0. Okay. So from equation, this equation, B1 equation, this equation, B1, B2, B3 equations will get B1 is equal to A1 by, sorry, A by 2 plus A by 2. B2 is also A by 2 plus A by 2. Okay. B3 is 1 by root 2 into A minus 1 by root 2 into A, as B3 is equal to 0, right? So it is equated to 0. That thing we have seen, right? So next is case 3, when input at port 1 is non-zero and at ports 2 and 3 it is 0. What happens then? So A1 is non-zero, so A1 is considered as not equal to 0. A2 and A3 are considered as 0. So then so depending on this, I'm writing this. So A1, A2 and A3 conditions. Okay, what happens to these equations at that time, right? So these cases are depending on this, right? So what happens when A2 is equal to 0, A3 is equal to 0 and A1 is not equal to 0? Then B1 is equal to A1 by 2, B2 is equal to A1 by 2, B3 is equal to minus A1 by root 2. In next class, we will discuss about the H-plane T, right? Thank you so much.